Hello, everyone. Thank you for tuning into my talk. Um, my name is Trinh Huynh, and I'm a senior at Clark University. Um, I've been working with Professor Arshad Kudrolli to build a magnetoelastic filament robot to help the study of Anguilliform swimming in soft sediment. In nature, limbless organisms such as eel and fishes use undulatory motion to navigate through various medium. And as you can see in the picture at the center, we have 4 types of swimming. And today we're going to talk especially about anguilliform swimming. Many microbial organisms, such as the Lumbriculus variegatus and the C. elegans, also utilize anguilliform swimming to navigate their respective medium as well. We fabricate a robot with a magnetic head attached to an elastomer body to investigate the locomotion in soft sediment. If you can see on the picture on the right here, there's like some sample of the robot. We also, the benefit of using a robotic system is that we can control parameters such as the elasticity of the filament and also the driving frequency that we can apply to the magnetic head. A little bit about the robot's fabrication. So in this diagram right here, we can see that the robot is comprised of 2 components, the magnetic head and also the elastic polyvinyl rod body. From top to bottom in this picture on the left, these version of the robot is have different Young modulus as you go from top to bottom, and the inertia and medium drag cause the body to deform depending on the applied frequency and the Young modulus of the elastomer. We also found out that across all these versions, the center of mass and length ratio is around 0.3. For the environment that we're interested in investigating is water and granular sediment. The type of granular particle that we're using is hydrogel, and our setup have the hydrogel bed have a depth of 0.5 to 2 centimeter. Hydrogel is a highly absorptive particle. When fully grown in water, it can grow to the size of 0.5 to 2 millimeter. Hydrogel also have the density that is close off that of water, and the benefit of using hydrogel is that because hydrogel have the similar refractive index as water, it's enable us to visualize the swimming dynamics of our robot system in real time through the medium. If you can see in this picture on the right, you can see the measuring rule can be observed through the hydrogel, saturated hydrogel. And the picture on the left indicate that the hydrogel without the saturated medium. So how does the actuation mechanism works? So if you can see from left to right, this is the experimental setup of the system. We have a pair of Helmholtz coil, a light source, which illuminate our system from the bottom, to the high-speed camera, which gonna capture the bird eye view of the system. We have a container with the sediment and water inside. The sediment depth, like we said before, it's about 0.3 to 2 centimeter deep. Since the magnetic head is much denser than the sediment, the swimming happens at the bottom of the container, as you can see right here on the side view. The filament itself is unusually buoyant, so we can keep it sort of level with the head itself. In the diagram in the middle, we can see the mechanism of the this robot a little closer. If we apply a alternative current to the Helmholtz coil is going to generate an alternative magnetic field, and that magnetic field cross with the magnetic moment of the magnetic head. It's going to generate alternative torque going into and out of the page, as you can see right here. As a result, the magnetic head is going to tilt left and right with the same frequency as the frequency of the alternative current, and the frequency applied is ranging from 1 Hz to 10 Hz. And in this video right here, it shows the high-speed capture of the worm from the top view, and it was captured at 100 frames per second. Moving along, so for the analysis of the speed and the shape of the this robotic system, we are interested in tracking the head, tail, and centroid location over time. The speed is obtained by taking the displacement of the centroid over the time interval of 1 second. For the amplitude of the body oscillation, there's 2 definitions. The first definition is that we consider the curvature of the filament and take the average of the curvature as the amplitude. While the second for the second definition, we consider the head movement in total as the head movement, the body movement, the head movement, the centroid movement, and the tail movement in total as the and average them as the amplitude of the worm. For the swimming velocity versus driving frequency, you can see that in water, the robot system travel much faster than hydrogel case. It's evident in the tracking. If you look on to the diagram on the right, you can see that over the same number of snapshots in 1 second, we can see that the robot in water cover more X displacement compared to the robot system in the hydrogel case. And in a similar research from our lab, we discovered that the sediment viscosity is around 2,000 times of water, and the Reynolds number in water is 3,000, and the Reynolds number in sediment is 0.5. So let's discuss about the first dimension of our amplitude, which is the body deformation. So as we increase the frequency, we can see that the amplitude also increase. At the frequency of 1 Hz, in both case, water and sediment, we can see that there's not much curvature to the body at all. But as we increase the frequency, the curvature become more and more prominent and behaving like a standing wave. And we're going to discuss about the second definition of the amplitude, which is the body rotation and deformation. For 1 Hz, similarly, we can see that the body behaving as a solid rod pivoting at the pivot location. As we increase the frequency, the exaggerated displacement in the y direction is become less and less. As a result, we can see that the amplitude decreases as we increase the frequency. One very interesting phenomenon that we also notice is that at low driving frequency, namely 1 Hz, the robot essentially rotates as a rigid body, as the elastic relaxation time scale is much smaller than the driving frequency. So the robot does not move forward at all because of Skalov theorem. But as we increase the relaxation timescale, the elastomer shape become more comparable to the oscillation period, and the body deform and show the dynamics as anguilliform swimming. Last but not least, we're also discussed about the effect of the elasticity on the swimming speed. As you can see right here, for a lower frequency range, namely from 1 Hz to 6 Hz, the Young modulus does not seem to affect the swimming speed, but as we increase our frequency, you can see that the swimming speed decreases as we increase the Young modulus. So in essence, in this experiment, we have constructed a soft robot that can move in both water and water-saturated sediment because of the transverse undulation from head to tail. And this system is driven by a magnetic head in oscillating magnetic field, give us the power to control the driving frequency. The shape of the body changes as we increase the frequency, so it changes from a rigid body rotation to anguilliform shape with uniform body amplitude from head to tail. And in the lowest frequency range, we see that the robot performs a reciprocal motion and does not move significantly at all. And the swimming speed in the sediments observed to also increase with the frequency. And finally, the elasticity showed to have impact on the swimming speed as we increase the driving frequency. So thank you for listening to my presentation. For further information, you can visit our website in this link right here. And if you have more questions, you can contact me at my email, Trinh Huynh@clarku.edu. Thank you for listening.